Okay, good morning, everyone. Welcome to the second day's morning session, which will have two talks. The first one will be by Stephen Wilson from the University of California at Santa Barbara. Steve, unfortunately, could not be with us due to some commitments there. We hope that next time he'll join us when we have something here. But in any case, thanks to Zoom, we could still have an interactive discussion and session. So let's welcome him, and he'll tell us more about unconventional charge correlations in Kagome metals. Steve, it's over to you now.
Great, thank you very much. And thanks for the invitation to attend and present at this very interesting conference this year. So I really appreciate it. And apologies to everybody for not being able to make it there in person. I had sort of a last minute family commitment crop up here. But I'm happy to still be able to connect with you remotely, even if it's suboptimal in terms of interactions. But what I do want to try and, I want to try and talk to you a bit about some of the work we've been looking at in two classes of Kagome metals, in particular, Kagome systems where there's Van Hoff singularities fairly close to the Fermi level. And I'll try and motivate why we're doing that and the two systems that I'll be talking to you about. So first off, just let me acknowledge the people who did all of the work. So Brendan Ortiz really launched the effort exploring Kagome metals in my group here. And he's now since moved on to a postdoc position at Oak Ridge National Lab. Ganesh Pokharel has done a substantial amount of work as well on a second system I'll be talking to you about, and he's now at the University of Western Georgia. And then students in my group, Linus Couch, Andrea Kapasalinas, and Stephen Gomez and Jaden Plum have done a lot of the scattering work that I'll be showing you as I go through the talk. Okay, great. So this is a Kagome conference, so I'm not going to belabor the background so much, but maybe for the students, just to remind everybody, so what the interests or one of the primary motivations of looking at electronic states in Kagome metals is that as sort of a generic kind of single orbital tight binding model, you get this interesting coexistence of features in the band structure comprised of, for instance, this sort of hopping interference-driven flat band, of which many systems or people are trying to develop systems where the Fermi level is within this flat band with the kind of interesting states predicted to form there. And then you also have Dirac crossings at the K points in the Brillouin zone, as well as a pair of saddle points that give rise to Van Hoff singularities at the M points in the Brillouin zone. And so here on the right, you can just see these sort of high symmetry cuts across these features. And you can see here, there's these two saddle points, which are inequivalent, meaning that one of them, for instance, is a so-called p-type or pure type Van Hoff singularity, where at that M point, for instance, the electronic wave function is derived from a single sublattice amongst the three sublattice Kagome net, whereas on the lower Van Hoff singularity is the M-type or mixed type, where you can have a mixture of of electronic wave functions from two different sublattices in the Kagome net. And so, okay, from a correlation physics standpoint, one wants to try and explore whether or not you can have nesting between these M-point Van Hoff singularities, where you should create peaks, and for instance, in the electronic susceptibility and potentially unconventional forms of electronic order. And indeed, at sort of looking at the Kagome lattice Hubbard model, there's a lot of interesting phases that are predicted if you can tune the Fermi level near these Van Hoff singularities. And so, for instance, predictions of different flavors of charge density, wave order, or charge bond order, as well as unconventional superconductivity are predicted to appear. And one of the oddities is that in sort of the weak coupling limit, if you're at this p-type Van Hoff singularity, then the on-site Coulomb interaction is severely diminished or vanishes, and it really promotes the influence of extended, nearest neighbor Coulomb interaction or further exchange terms. And so depending on the details, for instance, there are interesting phases, for instance, a so-called orbital flux phase or an imaginary charge density wave phase, which is a form of orbital antiferromagnetism, for instance, which maps to sort of some of the original to the states predicted by Haldane in honeycomb lattice systems, as well as instabilities, for instance, of unconventional superconductivity, for instance, D plus ID superconductivity, also originally sort of predicted sort of in honeycomb lattice system in this paper by Nankishore and Chubukov. And so the idea then is to look for Kagome systems that are close to these Van Hoff fillings and to find some type of experimental realization. And that's really sort of the focus of this talk, to try and talk about charge correlations in particular that form within two classes of systems. So for the first part of the talk, I'm going to talk to you about charge correlations that form in this so-called AV3 sp5 system. So it forms a Kagome net of vanadium. And then the second part of the talk, I'm going to talk to you about the so-called 166 material. And so these two systems realize very different charge instabilities. The 135 system on the left realizes primarily sort of an in-plane breathing mode of the Kagome net, whereas the one on the right, the lattice instability is primarily a chain instability out of the plane. And so I'll talk to you about sort of different flavors of kind of interesting charge correlations that form in these systems, which are also kind of connected to the Kagome sublattice in each system. Okay, so the first part I'm going to talk to you about these so-called 135 systems. I think there's been some talks earlier mentioning these systems yesterday. But so basically, just as a reminder, the building block, or the interesting physics, arises from the Kagome net of vanadium ions. The vanadium ions are very close together, so about around 2.7 angstroms apart. So you have delocalization across the Kagome net, and so these are sort of poly paramagnetic systems. So the local spin is sort of quenched, and the basic building block is you have this these V3 sp5 blocks, which are then spaced by these alkali layers. This is a quasi-two-dimensional layered structure, and so it's quasi-two-dimensional kind of chemically as well as electronically, which can in potential heighten some of the predicted effects of nesting between Van Hoff points. And so I guess the interest is that these systems indeed realize a band structure where you can see some features which are reminiscent of the Kagome band structure, for instance, from the vanadium net. So you can see a series of these saddle points at the M point coming from different vanadium orbitals, and in one case mixed with an antimony orbital. And the density of states at the Fermi level is really dominated by these vanadium states, with the exception of this gamma pocket here, which is derived from the antimony PZ orbitals. But these Van Hoff points at the DFT level are very close to the Fermi level, and so this sort of motivated some of the initial interest in these systems. And indeed, these systems realize correlation-driven physics. They're charge density wave superconductors. There are three different parent compounds, or flavors. You can change the A site. The A site can the alkali metal site can either be potassium, rubidium, or cesium. And depending on the A site, you get a superconducting transition, which is maximal for cesium at 2.5 Kelvin, and a higher temperature charge density wave instability, which is really maximized for rubidium at 104 Kelvin. Okay, so you have a much higher charge density wave onset, and out of the charge density wave phase, you see this lower temperature superconductivity onset. Okay, so the key questions is that whether or not any of this sort of exotic physics predicted from nested Van Hoff points in a Kagome lattice really manifests in these materials. And so I guess one of the questions explored by the community is really, does the charge density wave state break time reversal symmetry? Or another way of saying it, does the charge density wave have an imaginary component, or is there some orbital only antiferromagnetism present in these systems? Okay. And then the second question, of course, is the superconducting state born from this charge density wave phase unconventional? Okay. And then the third is sort of, are there any other intermediate states or instabilities as you go from the primary charge density wave instability all the way down to the superconducting phase? Okay. So this talk, since I have limited time, I'm going to focus on the charge correlations in the system, the real part eventually. But I will mention that there's been a substantial amount of work trying to explore to see if time reversal symmetry is actually broken in the charge density wave state in these systems. And I mean, I can't go through all of the data, but I'll just suffice to say that there's many different probes that sort of kind of report signatures of broken time reversal symmetry, ranging from USR measurements to scanning, tunneling, microscopy, and spectroscopy measurements, magnetotransport measurements, Kerr rotation measurements, as well as torque measurements in the charge density wave phase. But all of these, or the majority of these, are not without controversies, either in the interpretation of the data that comes that's being generated from the sample, or the reproducibility of the effect itself. But I will say there's been two sort of recent results which can perhaps address some of the reproducibility issues, in which the first I'll highlight, this is some very beautiful work by Vidya Madhavan's group at the University of Illinois, Urbana-Champaign, where they looked at the rubidium variant. And what they were able to do is they basically looked at the charge density wave phase on the surface of the system, and then basically Fourier transform that. And then when you do that, you can see the charge superlattice peaks that come from the CDW phase, which have inequivalent sort of Fourier weights. So kind of you can define a winding that goes from the highest to the lowest in terms of these three inequivalent endpoints. And the previous report originally by Zahida-san's group at Princeton was that a magnetic field could in fact couple to this charge density wave phase and switch the winding, okay? And so what Vidya was able to do is, first of all, to reproduce that magnetic field coupling in terms of switching this charge density wave phase. And then the second thing they were able to do is then they further showed that they could use a linearly polarized light. And when the polarization is along one of the endpoints, they can actually then similarly flip the sort of the apparent chirality on the surface with both a linear polarized light pulse, as well as an out-of-plane magnetic field. And so the claim there is that then they've sort of uncovered a piezomagnetic response in the system, which would imply that time reversal symmetry is broken in the zero field state. And then sort of in parallel, similar work by Philip Mull's group, where they basically create a small device. And what they showed is that when you take, in this case, cesium vanadium 3 antimony 5, and you prepare it in a strain-free state, and you look in the charge density wave phase, what you find is that you actually don't have any in-plane transport anisotropy that appears, okay? But then if you apply an out-of-plane magnetic field, then transport anisotropy turns on, okay? And so this is also sort of consistent with sort of a hidden piezomagnetic response in this system. And that goes to the fact that these systems can be highly sensitive to strain, unintentional strain or defects in crystals. And as part of my talk, we'll be showing you sort of the metastability and the impact of strain in the charge correlations of these systems. Okay, so now focusing on the real part of the charge density wave state. These are sort of the patterns of charge density wave. The structure in the charge density wave phase as determined via X-ray diffraction measurements. And so focusing here on rubidium and potassium on the middle and the right of the screen, what you can see is that what happens is in a single plane, a single Kagome plane, the Kagome lattice breathes in this 3Q distortion, which is a so-called trihexagonal distortion, where the Kagome net breathes into a pattern of triangles and hexagons. And then as you go from one layer to the next, they're phase shifted by half a unit cell, so the so-called pi phase shift. And what that does is it breaks the rotational symmetry of the unit cell, and you end up with a 2 by 2 by 2 three-dimensional charge density wave superstructure, okay? And so this pattern is the same for rubidium and potassium. But for the cesium system, if you look, there are actually charged superlattice peaks that are at a different wave vector as well. They're at the 2 by 2 by 4 kind of enlargement of the unit cell. And if you look at the average structure, meaning assuming a single phase across the whole sample, then you get a pattern of staggered and mixed trihexagonal layers, as well as the so-called Star of David, which is sort of the inverse version of that. Okay, the trihexagonal is sometimes called the inverse Star of David as well. Okay, so you have a much more complicated structure, and that's sort of what I'm going to be focusing on in this talk as we go, because the cesium system is somewhat unique from the other two in subtle ways. First of all, the charge density wave superstructure seems to be different. And this also seems to correlate that as you insert this larger alkali ion between the layers, at the same time, you also flip the ordering of the Van Hoff singularities, which are closest to the Fermi level. And so you end up with this dxz, dyz, which ends up closest in the cesium base variant versus the other two. Okay, so there's this subtle switch in the ordering of the Van Hoff singularities near the Fermi level, and that corresponds to the onset of seemingly a different pattern of charge density wave order. Okay, and I just want to further highlight, this is some photo emission work from Ricardo Komen's group, where they basically look at one of these Van Hove singularity is, I believe, the one with XZ and YZ character, and they can see that this is the one that's gapped as you go through the charge density wave state. Okay. Now, so the cesium system, it has this just kind of much more complicated charge density wave state. And then as you cool the system toward the superconducting phase, it also shows this very kind of complicated and rich hierarchy of energy scales as you cool into the system, okay? And so I can't go through them all, but suffice to say is that there's one energy scale, say around 60 Kelvin or so, where, for instance, you see the onset of, let's say, short lifetime lattice modes, for instance, in transient optical reflectivity measurements and Raman measurements. You also see the onset of sort of quasi-one-dimensional stripes on the surface of the system. And as you continue cooling the system around 35 Kelvin or so, there's a second stage where you kind of see the onset of quasi-one-dimensional features in the band structure as seen via quasi-particle interference spectra and STS measurements. NMR measurements also see some sort of local changes in the vanadium and antimony environments. And then as you continue cooling the system down even further, before you hit the superconducting phase, there's a report that you have an additional charge modulation at a wave vector that's like the so-called 4/3 A phase, which is reported to be sort of a signature of a pair density wave instability that modulates the superfluid density in the superconducting phase. Okay, so it has this complicated kind of structure, and it also seems to also have this more complicated starting phase. And so one of the oddities of that is that in the real part of the charge density wave for the cesium system, it seems to be marked by metastability, meaning there are different studies, I'm highlighting a few here, where if you quench the system through the charge density wave state or slowly cool it, then you suppress the relative intensity or modify the relative intensity of the 2x2x4 superstructure relative to the 2x2x2. Okay. And so in some systems, some of the original reports, for instance, the 2x2x4 superstructure wasn't even observed. And so it implies that this out-of-plane modulation is very sensitive. It's sort of a shallow minimum, I guess, in the energy landscape. And it depends on growth and disorder, as well as a thermal history of the system. And so one of the things that we wanted to do is to try and understand how, in real space, this modulation occurs. And so one of the techniques you can use is so-called dark field X-ray microscopy, which is basically kind of using a microscope to look at Bragg peaks and to see where the Bragg scattering comes from in real space. And so doing that, you can look at sort of just the structure. Okay, so this is not a charged superlattice peak. For instance, this is just a primary peak in the lattice. And you can see there's actually fine structure in the lattice, which is just coming from structural defects. And this is anomaly a pristine crystal. And so it suffices to say that you can see line defects, and along those line defects, we can see structural domains form. But then if you instead look at the distribution of intensity at a charged superlattice reflection, so this is the half position, which corresponds to the 2x2x2 superstructure. And then this is a half quarter reflection, which corresponds to the 2x2x4 superstructure. And you can look at the relative intensity of these and and if you just do some simple segmentation where one is dominant over the other, you can clearly see there's inhomogeneity locally on the length scale of, say, 50 microns or so in the lattice. And so what this is implying is that you have these sort of competing charge density wave phases, and they sort of phase separate locally in the system. And this is sort of consistent with this thermal hysteresis and the metastability in the material. And so we can look at this a number of different ways. If we just look now again at the whole crystal at once and just diffract from it with X-rays, you can take a look at how these charge correlations evolve as a function of fast cooling versus slow cooling through the charge density wave state. And so if you focus here on crystal 1, all I want to show you is that when you cool through the system quickly, when you cool through the transition quickly, so you quench it, then you suppress the ordering transition, and you mix the clusters of pixels which turn on at the same temperature between both 2x2x2 and 2x2x4 phases, okay? Whereas in the slow cooling or annealed phase, you don't have that strong mixing. They sort of have distinct onset temperatures. But the oddity is that we can then take another crystal, and if we take a razor blade and we just cut it to make it smaller, okay, to make it something that's more X-ray sized, okay. Then what we can see is that in that crystal, actually, the 2 by 2 by 4 peaks totally vanish, okay? And so this sort of implies that you have some subtle coupling to just mechanical deformation of mechanical strain, and we actually do see a subtle degradation of the crystallinity of the sample once we use a razor blade to sort of cut this crystal. So it's just to demonstrate that the charge density wave state in sort of the real component, basically the C-axis modulation in the cesium-based version is very sensitive to external perturbations. Okay, so another thing we can do is we can alloy the system, and we can try and change the filling to try and explore nearby instabilities, okay? And one of the approaches we've done is, okay, we can try and hole dope this system and to try and sweep the Van Hoek points closest to the Fermi level through the Fermi level to the extent that we're able to hole dope it. And we can do it two different ways. One is what we regard as sort of the cleanest way is you can replace the antimony site with tin, which is sort of not perturbing the Kagome net directly. And the other is you can replace the vanadium site with titanium, in which case you're putting a substitutional defect directly into the Kagome net. Okay, so looking at the hole doping phase diagram, what you find, first of all, is that the charge density wave phase is sort of rapidly suppressed, and you end up with sort of two domes in the superconducting TC, okay? And the first dome is within the charge density wave phase, and the second dome is outside of it. All right, if we look at charge correlations of these two domes, in the first dome, kind of slightly away from the first peak, what you can find is that if you, in reciprocal space, you have these charged superlattice peaks that are at these half-type positions, which is consistent with the 2 by 2 superstructure in the plane. But then when you start to look near this phase boundary where you have a minimum in TC, then you see that the charge correlations are sort of dramatically renormalized, and they split away from the half position into these incommensurate positions, and they become sort of diffuse in the direction of that they've split in reciprocal space. Okay, and so in a 3-domain model, then this would be sort of quasi one-dimensional correlations because they also become diffuse out of the plane. And just since there's not a ton of scattering work, I just want to emphasize how different the scattering looks between the undoped system. So this is the parent cesium vanadium 3 antimony 5 system, and the slightly doped, this is 5%. So this is only 5% holes per formula unit. So it's a reasonably small perturbation to the chemistry of the system. And you can see the dramatic change in the charge correlations, okay? And so in our picture, sort of we're pushing this close to what seems to be kind of a nearby sort of 1D instability where the charge correlations become incommensurate. As the lattice instability is suppressed via in the 2 by 2 charge density wave phase. Okay, and so one can then explore how these correlations evolve across the phase diagram. And so you can start with sort of light doping in this first dome, and then you can go out to the second dome where you still have these diffuse correlations. And then you can go all the way to where superconductivity vanishes. So in this regime, this is just a partial volume fraction superconductor. The charge correlations completely vanish. So they seem to vanish at the same point with superconductivity, and they undergo this evolution from the 2 by 2 correlations into the sort of what in our model is a sort of a quasi one-dimensional charge correlation volume. So what we can also do is you can then, instead of doing tin on the antimony site, you can do titanium on the vanadium site. And this is the phase diagram you get. And this is consistent with earlier phase diagrams that have been published. So basically, you don't get two explicit domes. You get a suppression and then a recovery once you exit the charge density wave phase. You still sort of get this sort of first order phase boundary near the two kind of, between the two maxima and superconductivity. And when you look at the charge correlation sort of across this phase diagram, what you see is something different. And so you basically, at light doping, you just see this 2 by 2 by 4 state, as well as 2 by 2 by 2 correlations. When you dope it a bit heavier, then you just see 2 by 2 by 2 correlations. But then when you get out into the second superconducting kind of region where there's no thermodynamic anomaly associated with the charge density wave state anymore, then we see no charge correlations. And so our current picture of this is the sort of the remnant kind of quasi 1D scattering we saw in the tin dope system is sort of quenched due to just putting the disorder onto the Kagome sites. That's sort of our current model, but we're still exploring that further. But what I want to just emphasize for this particular part of the talk is that, the cesium-135 system is sort of special in the class of these materials in that it seems, in its sort of pristine state, forms a metastable charge density wave phase, which is distinct from the kind of just the simple staggered trihexagonal stacking. And this seems to coincide with a switch in the Van Hoff singularities close to the Fermi level. It also has unique doping and pressure phase diagrams, which I didn't have a chance to talk about, which is also consistent with it undergoing a change in the charge density wave phase as you perturb the system. And so, yeah, so the doping evolution remains a mystery, and our current model is it's suggestive that there's a nearby kind of one-dimensional instability in the phase diagram. Okay. So now what we wanted to do is to try and find other Kagome nets based from vanadium with a similar band structure with Van Hoff points fairly close to the Fermi level, which are also non-magnetic. And so one interesting class to try and do this are these so-called 166 compounds. And so some people call these bilayer systems. So basically you have a Kagome net here and then a Kagome net here. They both have vanadium. And between these Kagome nets, you have a triangular lattice of rare earth ions. And you can make that triangular net of rare earth ions being non-magnetic by putting yttrium on it, for instance. But then you can also, in principle, control magnetism and interface it by adding magnetic dopants with these vanadium Kagome nets. And so the band structure of the yttrium system looks like the following. And again, you have these Van Hoff points, which are close to the Fermi level. And you also have more of a flat band feature, which is further away. And you can see, again, the Dirac points here at the K points. And by changing, for instance, you can put terbium or gadolinium or erbium, and you can get a lot of different magnetic behaviors in the system. But in the case of the yttrium compound, basically nothing happens. There's no phase transitions that have been identified in that system, okay? But David Mandras's group at the University of Tennessee, instead of putting yttrium in, put scandium, which is a smaller ion. And when he did that, then if you look in the susceptibility and resistivity and heat capacity, there's a transition that seems to form around 100 Kelvin. And in that transition, it can be mapped to a single Q distortion of this lattice, of this bilayer lattice at the K point in plane, which has a wave vector of a third, a third, a third, which is a √3 by √3 by 3 enlargement of the unit cell, okay? All right, so trying to understand how does this map to a transition, or does it map to any transitions in the 135 systems, or is it something unique? And so one of the, okay, I'm trying to, yes, you feel free to bug me if I'm running out of time. I kind of lost track of when we started.
You have 10 more minutes.
Oh, okay, sweet. I'll hurry. Okay. So this is the structure that's realized in the below the transition, below the charge order transition in the scandium 166 compound. But via DFT, the landscape, again, there's a lot of different competing distortions which can potentially occur. And the energetically favored one from a simple DFT approach is this √3 by 2. So the same in-plane reconstruction, but a shorter superlattice along the C-axis. And the key building blocks here of this distortion, as I mentioned earlier, it's a sort of a chain-like instability. I mean, you can see that the main motion of the atoms is really along the C-axis, so between the Kagome planes of these tin and scandium ions, okay, which kind of move collectively together, okay, in what I'll call like little trimer units, either up or down along the C-axis along these chains. And the interesting part about this system is that if you look at the wave vector associated with this unit cell, okay, this is not the one that forms below the charge order transition. If you look along this wave vector, even at room temperature, you see diffuse charge correlations at the wave vector, these are third, a third, a half type positions, okay? And as you cool down the system, you can see that you get the stronger diffuse scattering, it intensifies and it reaches a maximum right at the charge order transition and then sort of dissipates away as you cool below the charge order transition. Okay, and so what are the origins of these sort of seemingly sort of competing charge correlations, and how can we understand the charge physics in this system? And so One way of thinking about this is that you can put a smaller scandium ion in the system. And when you do, basically, if you look along the chain, the tin atoms basically sort of kind of come in and want to bond, and you form these trimer units, okay? And when you form this trimer instability, again, you'll form a chain of long and short bonds, okay? And so you can imagine I have a trimer here, and each of these trimers, the tin atoms, as the trimer forms, the tin atom tries to get pushed into the center of the Kagome net, okay, inside of a hexagon, and there's a steric effect, right? The tin atom wants to go in, and the vanadium atoms want to move away. Okay, and so then if you look at how you would tile that, if I can only move the trimer atoms up or down, which would correspond to the third, a third, a half wave vector, then it's frustrated in the plane, okay? If I just think about this Ising degree of freedom, I can't tile this triangular lattice with up and down, okay, without frustration. But instead, the system in the charge ordered phase switches, and along the chain, one trimer moves up, one trimer moves down, and one doesn't move at all. So then you can tile the triangular lattice in sort of like a three-state, like Potts type of tiling. Okay, but so that's sort of the idea of how you could have sort of lattice or steric frustration in the system. And so I guess one thing we'd want to do is how can you quantitatively show that this is what's going on? And so what we wanted to do is to understand, in this high temperature regime, is it true that we have these trimer units which is displacing up and down? And can we understand if the in-plane correlations are really driven by this frustrating Ising degree of freedom? And so the oddity here in that case is, can we capture this sort of kind of triangular shape of the scattering, of the diffuse scattering? Okay, so to do that, we did what's known as delta PDF analysis. It's basically just taking a large volume of X-ray scattering data, of diffuse data, and then punching out the Bragg peaks. And then that gives you, that removes the average structure. And then you can basically look at just the local, you can Fourier transform that into real space, and you can look at what's effectively a vector probability map of charge densities, which are displaced from the average structure. Okay, so the first thing we wanted to do is you can look at the motion of these trimers, and you can assume the low temperature trimer state and displacement, and then just do sort of a Monte Carlo type of model where you basically fix this but allow the trimer to displace up and down, and see if that can capture the delta PDF pattern that you see from the experimental data, from the transformed data. And indeed it does. And so by using this out of plane data, one can basically map and show that indeed you have these trimer units in the high temperature phase. Okay, so the ones that exist at low temperature are also fluctuating at high temperature. Okay, so for the in-plane diffuse scattering, we can do two things. We can do the reverse Monte Carlo and also forward Monte Carlo. And if we assume a two-dimensional limit, which is reasonable in this case because the correlations between the planes are very short range, then we can start with the reverse Monte Carlo analysis. And from that, you can basically get a pattern that matches the experiment. And this is just in what's generating this pattern of scattering are these sort of zigzag correlations within the plane, assuming just an Ising degree of freedom up and down of the tin atoms, basically. And so you can compare the delta PDF map, and I don't have time to go through all the details, but it matches to a good degree, okay? And then you can also do a forward Monte Carlo analysis. So if you think about a triangular lattice, the wave vector is, basically it's at a third, which means we need some zigzag phase. And if we assume some minimal model of J1, J2, J3 for a triangular lattice, and we take the limit where you have large J1, then we should have some constraints in terms of J3 having to be appreciable enough. Okay, and so we can do that, and using a forward Monte Carlo model, then one can also capture the sort of same type of behavior using the zigzag, again, using this J1, J2, J3 model. And one can capture the delta PDF pattern as well as the structure factor in these triangles, okay? And you can take it a bit further if you want to actually try and refine the values. And so Joe Pattison worked with my student Stephen Gomez, and they used this program Spinteract, where you can actually just refine interactions using this reaction field approach. And doing that, one can then fit the data globally and match and extract J1, J2, J3 parameters, as well as the intra-trimer and intra-trimer coupling between tin atoms. And so this is all consistent. And just to show you, the forward Monte Carlo and the experiment match very well. And it really captures the key features of the diffuse scattering, which is consistent with this sort of Ising-like degree of freedom. And this is, I just want to highlight, this is some other work where you can also see these triangles in the diffuse scattering of this system. And so, yeah, so the last thing I would just highlight is that this diffuse scattering at high temperature, these sort of short-range Ising-like correlations, seemingly impact the electronic properties. There's sort of a high temperature pseudo-gap-like behavior that's reported in the system, as well as a larger charge gap that seems to be picked up in STM. And so potentially these two things are coupled. And I'll just conclude here by saying that, hopefully I gave you an overview. There's different classes of Kagome metals with distinct pathways to charge order. One is a chain instability that I just talked about, and the other is this in-plane kind of 3Q distortion with some interlayer correlations. And the 135 system, I already talked about, but then the second class, I think the scandium, it shows a different kind of interesting pattern of charge order with frustrated charge correlations, but also that frustration is due to the Kagome network. And with that, I'll thank you very much for your attention.
Any questions, comments? Yeah.
Okay. Okay. Can you show me the your what's it, two sample comparison coming from X-ray based macroscopy data? You said something is odd. Is it? Oh yes, yes. So I'm curious. In my mind, I have been thinking that the CDW correlation within the plane and outer plane not necessarily identical, because the energy scale of the in-plane CDW must be different from the outer plane. So when I look at your data, I just was thinking about this old idea in my mind. So do you see any different energy scale in this kind of analysis, whatever it may be? So that's my just big question.
Yeah, sure. So I think, first of all, to address your first point, I mean, I totally agree. The in-plane energy scale is much different than the out-of-plane, right? And so the in-plane is this basically breathing mode, either into a trihexagonal or inverse or Star of David type of distortion, and how these layer along the c-axis seems to be a much lower energy scale that's easily perturbed. So now to the question about, do we see different energy scales?
Oh yeah.
If you take a fixed cooling rate in the cesium system, and you look, and we're not the only ones who have seen this. There's another group that's seen this. If you cool through the CDW and you look at the onset of charge order, okay, via diffraction at different wave vectors with different out-of-plane wave vectors, okay, so same in-plane wave vector, but out-of-plane wave vectors are different. You see the onset of charge order at different temperatures, slightly different temperatures. They can be as far spaced as 10 Kelvin or something, depending on how fast you're cooling.
Mm.
So that sort of like stages in, but one distinction I will say is that it's, for the cesium system at least, it doesn't seem like the in-plane charge order pattern at least seems to be different from a couple of different probes, meaning you seem to have a mixture of both Star of David and inverse Star of David layers. And that's seen via like average structure analysis from X-ray, as well as, for instance, photo emission, angle resolve photo emission claims they see band folding consistent with that. Yeah, so that seems to be another distinction, perhaps.
Okay. Have you ever seen any data from, the potassium and also rubidium, or?
They don't do this.
Okay.
They seem to, yeah, you don't have this metastability in those systems as far as we know.
Okay, thank you.
Yeah.
Oh, hi, Stephen. It's Bruce Golan speaking. Nice
Hi, Bruce.
Nice to talk. Yeah. So I had actually a couple of questions. So at the very beginning, you showed this STM measurement where you had the Fourier transform, and this was reproducing some earlier data, I think, from Hassan, and where the pattern has been interpreted in terms of a chiral or chirality associated with the charge density wave. And I guess I had two questions here. So one is, am I right to associate these the peaks in the Fourier transforms with basically a structure factor, the same type of structure factor that you would measure in X-ray scattering, or is that not correct? That's one question.
That's the way I view it, at least. I mean, yeah, they're taking the real space data and Fourier transforming it, but they can keep track of the phase. So I don't know if there's any other information in there, but yeah, that's the way I view it, at least. I agree with you there.
So anyway, so I was gonna ask, is there anything in the low temperature X-ray data that you've taken that can be associated with a chirality for the charge density wave?
Yeah, that's hard to. That's a great question. And that's hard for us. It's been hard for us to say with any confidence because of domain effects and the difficulty of precluding them. And so, yeah, we haven't been able to say a sharp statement about whether or not one can see chirality with just, X-ray diffraction on a bulk sample. I think one would need a really small, like what you can hopefully be a single domain piece, and then maybe do something a bit more in depth, or maybe TEM or something is a better way to go. Yeah.
And well, at least peripherally related, have you done any resonant X-ray scattering where you can tune to a resonance of, say, vanadium or antimony or these sorts of things, and sort of try to put some of the phase information back in?
Yeah, we haven't done that. There have been others that have seen, like, for instance, I know there's some work looking at the antimony L-edge, I think, and claiming to see a different behavior on resonance at the antimony L-edge versus the kind of the off-resonance scattering behavior. I think there's a recent paper that was posted, and I can send it to you, where they're looking at the vanadium L-edge, I believe, and they claim to see some signatures of a chirality. I haven't had a chance to read it. I saw it today, so I'll send it to you.
Okay. Yeah, thanks very much.
Any further questions or comments? If not, then let's thank Steve again for a very nice talk.